very soon, because once I start recording, it then says can't detect technology. It's supposed to track me. It's hopefully not blocking too many people, but anybody who comes in late, that's their fault, and they can take that nice seat. So I thought today we would talk a lot about sequences and series, and the idea is to talk about the mathematics behind it, talk about some of the applications, what we can do with these, how do we prove these results, why do we need to be careful. So the first item is convergence. And then I know when I was a graduate student, we would have all hands on deck the day we did epsilon delta proofs and trying to do things rigorously. Do you do this in calculus here? Do you do the epsilon deltas? Or do you do the pictures and the hand waving?
Yeah, that's right. For the AB class, I do the hand waving.
Right. So the first question is, what do we mean for something to be continuous? What do we mean for something to be converging? And so frequently we would say, xn converges to x if for all epsilon greater than 0, there exists an n such that for all n greater than or equal to n, we have xn minus x is less than epsilon. So as we go further and further down, we're getting closer and closer to one value. So then the first thing you would show is that if a limit exists, the limit is unique. You can't converge to two different things. And just pictorially imagine it converged to x and it converged to x tilde. Well, there's got to be then some distance between them. So you choose your epsilon so small that if you add epsilon here to x tilde plus epsilon and you subtract it over here to x minus epsilon, there's still a separation. So eventually I've got to be somewhere through here, I've got to be somewhere through here. They're so well separated I can't be in both. So if a limit exists, the limit is at least unique. Then the question becomes, how do you determine if the limit exists? One of the best ways is if you can actually point to what it's converging to. And so my kids have been having fun recently with 0.99999, or just drawing it like this, is the same as 1. And so one way to do this is really, xn would be the sum, m goes from 0 to n of, say, I guess I'm going from 1/10, 9/10, 1/10 to the n. And if I wanted to subtract this, look at 1 minus xn, I can quantify exactly how small that is. And I can see that that's going to 0. And here's an example of a sequence where I know the limit. So the biggest sequence that we always look at is the geometric series. So I don't think we did this the last time, the geometric series. This is the most important one to know. Basically, do you do the comparison test in your classes?
Only in BC.
Only in BC, OK. So a lot of the things like the ratio test, the root test, they're all really applications of the comparison test where you compare things to a geometric series. So a geometric series is defined as 1 plus x squared plus x cubed plus ... And this is 1 over 1 minus x if the absolute value of x is less than 1. So there's a couple of ways to prove it. I'm going to do the standard proof first, then I'm going to do the basketball proof second. And I love doing the basketball proof. I actually have students shooting, and whoever wins is actually excused from homework. So it gets a nice class atmosphere. So let's define Sn to be 1 plus x all the way up to xn. Then if I multiply it by x, I'm basically just shifting everything down 1. So 1 goes to x goes to x squared, x to the n minus 1 goes to x to the n, and I have x to the n plus 1. So now when I subtract, I get 1 minus x times Sn is 1 plus xn plus 1. I'm sorry, 1 minus. And then just solving, we get the sum xn is 1 minus xn plus 1 over 1 minus x. Or a better way of writing this is it's 1 over 1 minus x plus x to the n plus 1 over 1 minus x. And this goes back to what we were talking a moment ago. If you can see what the limit is. Yes, this should be a minus. Thank you. If you can see what the limit is, you can then say, is my distance to that limit getting smaller and smaller and smaller? So here for the geometric series, I can point to the limit is 1 over 1 minus x. And then here is the error term. And you can see that if the absolute value of x is less than 1, when I raise x to a higher and higher power, this is going to get smaller and smaller and smaller, and this will tend to 0. So the geometric series is wonderful for a variety of reasons. There's a lot of things in mathematics that are valid, but actually require significant proof. And so one of the big ones is people often think if you have a sum, you can say the derivative of a sum is the sum of the derivatives. So this is something you prove in calculus. But you only prove it for finite sums. So what if you have an infinite sum? Is the sum rule still valid? And sometimes yes, sometimes no. The geometric series is one of the few places where this is valid. So I'll do that as an example of how you have to be careful. I'll then show how you can actually create infinitely many more formulas just from this. There's a lot you can do from this. And so I'm hoping to very quickly get to stuff you haven't seen. Have you seen the proof of the geometric series formula from playing basketball? OK, so the age distribution between myself and you is not as bad as it is between me and my students. So I think you will all understand who Larry Bird is. Yes. And who I won't do Michael Jordan. I will do Magic Johnson. OK, so Bird and Johnson are playing a game of basketball. Probably should do Jordan because of the old basketball commercials for the McDonald's bag. First one to get a basket wins. Because I'm a mathematician, I'm going to idealize things. Larry Bird always shoots, and he always has the same probability of making a basket. Never tires. Magic Johnson shoots, always has the same probability of making a basket, never tires. Bird will go first because I'm biased. I prefer the Celtics to the Lakers, so we'll let Bird shoot first. So probability Bird gets basket. I'll call it P. You could also call it P sub B for probability of Bird. Either one is fine. And you want to think, what notation do you want to do? Do you want to put a B for Bird and then a J for Johnson? So probability Magic gets basket is Q. Often in probability, you have Q being 1 minus P, the probability of the complementary event. Here I'm going to just say P and Q are the two probabilities. And I want to calculate what is the probability Bird wins. So let's let x be the probability Bird wins. So I'm going to write x as a sum of independent events. So Bird could win on his first shot. So what's the probability Bird wins on his first shot? P. OK. Not so bad.
Yeah, I can do that.
What's the probability Bird wins on his second shot?
1 minus P plus 1 minus Q.
So if Bird is actually shooting, then yes, he has a probability P of making the basket, but he's got to get to his second shot. So they both have to miss. So first Bird misses, then Magic misses, then Bird hits it. So this is the probability Bird wins on his first shot, probability Bird wins on his second shot. What's the probability Bird wins on his third shot?
1 minus P squared, 1 minus P squared, 8.
Right, so I'm going to just square that whole thing. So we really want to introduce the symbol for 1 minus P times 1 minus Q. Since we're doing a geometric series, you often use R for the common ratio. So let's let R be 1 minus P, 1 minus Q. This is the Boston area. That's a close enough approximation to how that letter is pronounced. So we get x is P plus RP plus R squared P plus R cubed P plus dot, 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 dot.
Okay, I get the math.
Right.
What's the situation? I'm confused on the situation.
So the situation is Bird and Magic are just alternating shooting baskets. First one to get a basket wins.
Okay, so for that's the piece I didn't.
Okay, yeah,
Why
yes.
looking if he loses, yeah, so-
Right,
got it.
yes.
Perfect.
Now, I could ask you, what's the probability that Magic wins? So you could actually go through the whole rigmarole. Well, first Bird misses and then Magic hits. But of course, if Bird wins with probability x, Magic wins with probability 1 minus x. Then you could also modify the game, and this is a nice problem to give your students. What's the probability Bird gets 2 baskets before Magic gets 1? And then you have to start breaking things into a tree. Once Bird gets a basket, it's almost like they're playing the game again, except now Magic shoots first. So there's some nice additional problems you can do from this. So if we knew the geometric series, we would be done because we get x is p 1 plus r squared plus r cubed. But I'm assuming we don't know the geometric series. And I'm going to use this to deduce the geometric series, and I'm going to use one of the best insights we have in game theory. If you return to a previous state, frequently all that matters is that you're in that state. It doesn't matter how you got there. There is actually ridiculous situations in baseball where runners have stolen first. So somebody actually ran to second and got confused and ran back to first base. It's happened occasionally in baseball. It no longer matters that they stole second. All that matters is we have a runner on first. It doesn't matter how they got there. Let's calculate the probability Bird wins again. Bird could win on his first shot, which happens with probability P. Now imagine Bird misses and Magic misses. So they both miss. From this point onward, after they both miss, what is the probability that Bird wins from this point onward? No, P is the probability Bird wins on this shot. It's X. Right? So we'll see if it tracks me as I get the marker. So because they both missed, we're starting the game all over again. So what we've done is we've converted an infinite sum to just two terms. This is because we have a memoryless process. So memoryless process. So this is absolutely amazing. It doesn't matter how we got here. I could have had 12 misses by Bird and 12 misses by Magic. And then if Bird has the ball, the probability Bird makes the basket is just X. So we now know X equals P plus Rx. Well, we can solve for X. This means 1 minus R times X equals P. So X is equal to P 1 over 1 minus R. So this expression over here, our infinite geometric series sum, must be the same as this. So this is another way to prove the geometric series formula. Now, it's not quite as good of a proof of this as the other one. So this is a really subtle point. This is where it's a disadvantage that you have a theorist in the room. You always want to look at what have you assumed. How far can you push an argument? If you really want good math, look at the formula that destroyed Wall Street, and how around 2008, 2009, a lot of people were just using formulas and not being that concerned as to whether or not they have a right to use that formula. Formula seems to be doing well. What are the assumptions? When we proved the geometric series formula for the first time, all we needed was that x was less than 1 in absolute value. And as long as x was less than 1 in absolute value, this argument applied. What do we need to assume about R over here for this argument to work? What must be true about R?
It doesn't equal 1.
So R can't be 1. Now what would it mean for R to be 1? Well, for R to be 1, we would have P equals 0 and Q equals 0. So that means Bird and Magic suck. There's no other way to phrase this. And that means neither one of them will ever get a basket. So if we have the situation where R equals 1, we get the probability that Bird wins is P over 1 minus 1 minus R. Well, but P is 0, and 1 minus R is, so we have 0 over 0. Good. So at least in the situation where they both suck, the formula can't tell us anything. What else must we assume about R? So R is definitely not 1. What else must be true about the expression 1 minus P, 1 minus Q? Greater than or equal to 0. So for instance, either Bird or Magic could have probability 1. And if that's the case, then the game is fairly easy to analyze. Whoever has probability 1, once they shoot, the game's over. So R must be non-negative. Whereas in the original geometric series formula, that argument actually worked if R was negative as well. So the question is, what would you do if R was negative? How would you tweak this? Well, I'll leave this as a homework problem or as an exercise. Split things up into the evens and the odds. If you look at 1 plus R squared plus R to the 4th plus R to the 6th, all the even powered terms will be non-negative. And then if you look at the odds, r cubed, r to the fifth, you pull out an r from them, and then now you have the same thing again. So you can actually break it up into two situations that you know. So it's a nice homework problem. Figure out how to handle the odd case. Okay. Hello? Any other questions on the proof of the geometric series formula? So I want to just use this to justify differentiating an infinite sum. And this is just some of the stuff you have to be really careful about in advanced mathematics. I had a phenomenal freshman physics professor who said one day, the following step takes 6 weeks to justify in a math class. Moving on, we see, and just the way he phrased moving on. So in general, we cannot just interchange operations. So if we want to change, we have this infinite sum, we want to take the derivative of the infinite sum, we can't always do that. But for geometric series, there's something nice we can do. So imagine f of x is 1 plus x squared, going off to infinity. And I want to justify differentiating term by term. Here's the trick I can do. F of x is the same as 1 plus x squared plus x to the n plus x to the n plus 1 plus x to the n plus 2 going off to infinity. Okay, I've just explicitly written in a few terms. I'm not really doing that much right now. What can you tell me about the tail of this geometric series?
X to the n times.
Yeah. So it's just 1 plus x squared plus x to the n plus, I can now pull out an x to the n plus 1, and now I have a geometric series. 1 plus x squared. The tail of a geometric series is a geometric series. This is one of the reasons we love the geometric series so much. Okay, why is this useful? Well, this is now 1 plus x squared plus x to the n. And now we can use the geometric series formula here. And now if we want to differentiate this term by term, we can. I'm just making sure it's recording. It says it is. OK. That's the best I can do. We can differentiate term by term because it's now a finite sum. And so we get f prime of x. OK, we get derivative of 1 is 0, derivative of x is 1, 2x plus 3x squared plus n x to the n minus 1. And now we get to do the quotient rule. Right? So it's derivative of top times the bottom, right? N plus 1, x to the n, 1 minus x to the n plus 1. And then the derivative of this is just negative 1. And then we divide by 1 minus x. And now we can look and see, well, what happens as we let n get larger and larger and larger? Well, we have an n plus 1 over here that worries me a little bit because that's going to infinity. But as long as x is strictly less than 1, this quantity here is going to be getting exponentially smaller. So think of x as even 1/2, 3/4, 5/8, anything like that. This is going to be decaying far, far faster than n is going to grow. And so what you can see is, with a little bit of work, this part goes to 0 as n goes to infinity.
Sorry, can you say when the denominator is not squared? I must have.
Oh, I'm sorry?
Okay.
Yeah, I think it was just the way the lighting was hitting it. This is me sadly being a little bit careless because I know the term doesn't matter. But yes, you're absolutely correct. It should be squared down below. Yep. And so that's what's really nice about the geometric series. The tail is a geometric series itself. So the question is, why might you care about this? So how many of you have heard of the phrase differentiating identities? OK, good. So identities are the bread and butter of mathematics. We work really hard to prove something. I gave you 2 proofs of the geometric series. I feel like I'm selling something now on like one of these home shopping networks, and the first 5 mathematicians get a pair of Ginsu knives as well.
We help you back.
You guys know where Lisa is?
Math lab or Karen's office or her office?
Doesn't she teach? No, this is my own.
I was really impressed. I said the word knives, and all of a sudden there was somebody with a walkie-talkie in the room. I mean, this is security.
There's a camera following you.
Yes. Yes, there actually is a camera following me around, as you know.
Maybe just really want to take the class now, so you're getting the live feed.
Right. So the idea of differentiating identities, if you spend a lot of time proving an equality, wouldn't it be nice to generate new equalities from it? And so the idea is we're going to be able to prove infinitely many equalities now that we know the geometric series formula. And it goes as follows. So I'm going to assume now that I have justified to you term-by-term differentiation. So this sum is the same as 1 over 1 minus x. So let's take, for instance, if I take f of 1/2, I get 1 plus a half plus a fourth plus an eighth, which is 1 over 1 minus a half, which is 2. Let's take the derivative of both sides. And so I've got derivative of 1 is 0, derivative of x is 1, derivative of 2x, the x squared is 2x, plus 3x squared, plus 4x cubed. And then when I take the derivative of this, I'll get negative 1 minus x to the negative 2 with a negative 1 from that. So I get 1 over 1 minus x squared. Now, one thing that's a little bit annoying is I've dropped the powers of x. So what we sometimes do is we might just multiply both sides by x. And so I'll get x plus 2x squared plus 3x cubed plus 4x to the fourth equals x over 1 minus x squared. So what I'm really doing is to get from here to here, I'm applying the operator x times the derivative of x. So the derivative of x lowers the power of x by 1, then x brings it back up to 1. This is now a new identity. And identities like this occur all the time in probability. So now if I want to evaluate what happens at the point 1/2, I look at 1/2 f prime of 1/2. That's going to be 1/2 plus 2 over 2 squared plus 3 over 2 cubed plus 4 over 2 to the fourth equals 1/2 over 1 minus 1/2 squared, which amazingly is also 2. It's not always going to be equal to 2. But the idea is we can now create more identities like this from 1. And quantities like this occur all the time in probability. So if there's interest, maybe for the third session, we can talk about elements of probability. How do you actually calculate probabilities of events? So frequently, you might have something where the probability of something happening, probability that it happens once is maybe 1/2, twice is 1/4, 3 times is 1/8, 4 times is 1/16, some kind of geometric decay. And you might want to know what's the average value. And so the average value is you would take each of the possible numbers and you would weight it by the probability it occurs. So this is a value of 1 weighted by its probability 1/2. This is a value of 2 weighted by its probability 1/4. This is a value of 3 weighted by its probability 1/8. And so this will give you the average value of this process. And you can use ideas like this to calculate all these quantities very easily. And so there's a lot of different stuff we can do with these sequences and series. But it all came down to, we started with the geometric series, which we understood. We knew what the limit was. And this is actually going to be a big theme for today, is the fact that we had this closed form expression. It's equal to 1 over 1 minus x. It's not just that it converges. It converges to something we know, and it's something that we can work with. 1 over 1 minus x is not a horrendous object. It's almost the nicest thing you could hope for on the other side. Okay, any questions on this part up till now? Okay, so I'm not going to go into all the different tests, the ratio test, the root test, whatnot, but they all come down to understanding the geometric series. I was going to sketch a proof of the fundamental theorem of calculus, because that gives us the ability to talk about lower sums, upper sums. Yes?
Wait, can you say one more time about the probability at the end?
Sure. So let's say we have something, the probability, my random variable x takes on the value of n is 1 over 2 to the n, where n is in the set 0, I'm sorry, here I'm doing it 1, 2, 3. So a nice example of this is I'm tossing a fair coin, and I keep tossing it until I get a head. How many times do I have to toss before I get my first head? Half the time I get a head on my first toss. Fourth, I get it on 2 tosses. Eighth on my 3rd toss. And now I could ask, what's the average value? So the expected value, expected number of heads. Sometimes it's called the average number of heads. Sometimes it's called mu of the mean. Sometimes it's written expectation of x. And it's just going to be the sum, and it goes from 1 to infinity, of n times the probability that x equals n. And so this is how you would calculate the average value of this process. So if I flip a fair coin, on average, how many flips do I need before I get my first head? So whenever you get an answer, you should always ask, is it reasonable? So can anybody tell me why 2 might be a reasonable answer? So
It should take you 2 to get an option.
you have 2 options. You have heads and tails. But are you surprised that it's not a little bit below 2? Because we can get a head on our first toss, and that's a 1.
But you can also get it on the 3rd or 4th or 5th. You can't get it on the 0.
Can't get it on the 0. And so when you have to wait very long, that's going to inflate the mean. But those are given very low probabilities, so they're not going to push it too far. And by the time you toss it 3 or 4 times, you've got most of your probability. So this is a positive number. It's greater than 1, which is good because you're not guaranteed to have it after 1 toss. And it's not too high. And you've got a 50% chance of getting it just after 1 toss. So the answer is quite reasonable. If you know statistics, you can also use stuff like this to calculate the variance or the standard deviation, or to calculate the moments. It all comes down to being able to evaluate sums like this. So the sums that you're teaching in calculus, these become crucial in calculating these probabilities. Okay. Other questions on geometric series? Okay, so what I want to do now is I want to talk about the intermediate value theorem, which leads into the mean value theorem, which is, I think, my favorite theorem from calculus, and then go into the fundamental theorem of calculus. So how many of you prove the intermediate value theorem in a class? Okay. How do you do the proof? Do you?
Asking me this one out.
So.
I can't answer you off the top of my head.
So often denoted IVT. So the intermediate value theorem says that if you have a continuous function, so f is continuous, if f of a is less than f of b, then for all c between f of a and f of b, there exists a little c in the interval ab such that f of c equals c. Another way of phrasing this is there's no jumps. So if you start here at a, and here's your value, f of a down here, and here's b, and here's your value, f of b up here. So here's f of a, here's f of b. You give me any intermediate value, there has to be some point down here between a and b where my function takes on that value. No matter how I try to draw this, if it's continuous, and there could be multiple points, but there has to be at least one point where the value of my function at that point is the intermediate value. Another way of saying this is if you start 10 miles from home and you end 20 miles from home, at some point you were 15 miles from home. At some point you were 17 miles from home. You move continuously. There's no transporter. Right? That's why we have to assume f is continuous. If f did not have to be continuous, well, I could just have it be all the way here and then halfway through maybe shift to being over there. So the question is, how do you prove this rigorously? And so a lot of it depends on what do you want to assume and how much detail do you want to get into. I'm going to content myself with a quick sketch of a proof. And the reason I want to do it this way is it goes back to something we did last time when we were talking about divide and conquer. So proof by divide and conquer.
So, sorry, can I
Yep. Yes.
So, one of the things that always comes up, you wrote.
Oh, the symbols?
No.
Oh, okay.
No. You have to, because I'm looking at one of the things that always comes up is that some definitions say that x has to be on a closed interval.
Right.
That way you can deal with the possibility of a horizontal line.
Right.
Can you comment on that?
So I wrote here very explicitly that f of a is strictly less than f of b.
Okay.
And so I'm choosing some point c between f of a and f of b. So it can't be a, because at a I know I'm f of a, and it can't be b. If I allowed c to actually either be f of a or f of b, then I would have to do the closed interval. So if I said instead, imagine my value of c is in the closed interval f of a, f of b.
Yep.
Then I would have to say little c is in the closed interval a, b, because I could just have the straight line. But I'm now saying c is not equal to either a, f of a, or f of b, because it's not that hard for me to find a input that goes to f of a. I'll just take a. So when we get to the mean value theorem, one of the big points is that there's a point between a and b. And that is important for some applications, that it's not exactly. Okay. So here's the proof. So we did divide and conquer last time. So here's a, here's b, and let's say here's f of b, and here's f of a down here. And for simplicity, I'm going to just do the case where big C equals 0. I just want to find a place where it hits the axis. If I wanted to do C equals 1, it would be a very similar argument. What I'll do is I'll look at the midpoint. And just to make things even nicer, let's make that 0, and let's make that 1, just so I can do the fractions in my head. I'll still get them wrong, but I should be able to do them in my head at least. All right, so here's 0 and 1. Let's look at the midpoint 1/2. If it happens to be 0, great, we're done. If not, then it's either positive or negative. And if it's negative, then we'll look between 1/2 and 1. And if it's positive, we'll look between 0 and 1/2. And so what we'll do is we'll define a sequence of intervals. A0, B0 will be the interval 0, 1. And then maybe A1, B1, let's say it was negative over here, would be the interval 1/2, 1. And we keep going like this. So every time we do it, our interval halves in size. And so we get a sequence of points an and bn, such that f of an is less than 0 is less than f of bn. So this is where it's extremely important. My left endpoint is always negative. My right endpoint is always positive. One of two things happen. One possibility is I can't do this forever. Well, the only way it would break down is if one of my endpoints actually evaluates to 0, which is great because I'm trying to find a point that evaluates to 0. So if an endpoint maps to 0, we're done. Else, we have f of an is always less than 0, is always less than f of bn, but an minus bn goes to 0. Because every time we do it, the length of the interval halves. Well, by continuity, and this is where it gets painful. And this is where you have to decide how much detail do you want to give to an intuitively obvious statement in a high school class. This is where real analysis comes in to do things very carefully, very rigorously. We have an interval that's shrinking, so the two endpoints should be converging to a common value. And it's possible that maybe first I move this endpoint, then this endpoint, then this endpoint, then this. Maybe they alternate in terms of which one moves, or maybe I do something first this one moves 3 times, and this one moves once, then this moves 4 times, and this moves once. But they are going to converge to a common value. So an, bn converge to some special point. Let's call that point C. And what do we know about the value of the function at c? Well, c is going to be greater than or equal to each of the an's. So we know, for all n, f of an is less than c. I'm sorry, is less than f of c. And we also know that f of c is going to be less than or equal to f of bn. But in the limit, an goes to c. So if this was less than 0, we'd have a problem. Because over here, it's got to be positive. Similarly, if it was positive, we would have a problem over here. And this is the part where it seems intuitively obvious just how much do you want to do. There's got to be some value at c. If it's positive, then you're going to have a contradiction, because if it's positive, eventually an has to be so close to it that f of an will be positive as well. That's what it means to be converging. You have some special value here, c. If f of c was over here, then you choose a really small window about c. And once n is so large, you land in here, f of an would have to be positive, and that contradicts f of an being negative. So this is the proof of the intermediate value theorem. Now that we have the intermediate value theorem, we can use it to prove the mean value theorem. And then I know one of the things I was asked to do was to do Taylor's theorem. And so this is actually one of the things that made me into a mathematician. I had this is being recorded. I'll save that story for when this is not being recorded. Yes?
Kind of pedagogical.
Yes.
So to finish this proof, you feel messy and ugly and you very, very detailed.
So, if we zoom in, we have the point C. We have a sequence of points an converging to C, and we have a sequence of points bn converging to C. So you first have to prove that there actually exists a unique point. But we know each of the an's moves at most 1 over 2 to the n to get to the next one. So it's bounded by the geometric series. We're going back to the geometric series. So the an's, it's a subset of a geometric series. So the an's will go up at most a certain amount, and the an's will converge to something. Similarly, the bn's move down by at most the geometric part, and they'll converge to something.
So what I was asking was like when you teach it to undergraduates, where do you stop the proof?
I've never taught real analysis, so I've only taught this in a calculus class, and this is the level of proof I would give. In a real analysis class, I would be a little bit more rigorous with the epsilons and deltas, and I would say, if it converged to a positive value here, then there's some small little neighborhood here where, because my function is continuous, you give me an epsilon, and I can find a delta such that I will still be positive. And now once an gets in that range, f of an will be positive. And that would be the epsilon delta contradiction. Okay, so what I want to do now is I'll do the mean value theorem, and then I'll do Taylor's theorem. So how many of you teach Taylor's theorem? Taylor series? Just Jill? Okay. But we saw an application of Taylor's theorem last time, or at least the first order Taylor's theorem, when we did the birthday problem, when we took the logarithm and then we expanded the log of 1 minus x to estimate it's around 22 people before you have a 50-50 chance. So nice thing is I just have to change one letter. So the mean value theorem. How many of you teach the fundamental theorem of calculus, though? Okay. How many of you have watched Friends? I don't know if I've already made this joke. Except for 1 or 2 episodes, every episode of Friends is named how?
Yeah.
The one with. And so when I teach the proof of the fundamental theorem of calculus, I titled the lecture, The One with the Mean Value Theorem. It's essentially all applications of the mean value theorem. You can avoid the mean value theorem by taking real analysis and using uniform continuity. Or you can just say, you know what, let's just assume my function's differentiable and bounded, and let's go from there. And so here's the mean value theorem. So let's say f is continuously differentiable, and I'll assume f prime is also continuous. This is more than I need, but I prefer to just assume a little bit more. Then there exists a C in the interval AB such that f prime of C is equal to f of B minus f of A over B minus A. Or equivalently, f of B minus f of A is f prime of C times B minus A. So the way this is typically done pictorially, I've got something like this. Here is A, here is B. F of B minus f of A over B minus A, that's the slope of the line connecting B and A. This is just saying that there must be some point C where the slope at C is equal to the slope in this whole area. The other way of looking at this is, imagine this is a distance plot. So over here, you always want to tell a story. This is time, this is distance. So what would the slope represent if this is a story? Speed. So this is the slope f of B minus f of A over B minus A is my average speed. So here's, by continuity, if speed is continuous, you must be traveling the average speed at some point. Imagine you're always traveling below the average speed. So if the average speed is 50 and you're always traveling below 50, how can you get to 50? Conversely, imagine you're always traveling above 50. So this is the intermediate value theorem. So I can give you, if you want, but I probably won't, the rigorous mathematical proof doing it with symbols and whatnot. But here's the story proof. It follows immediately by the intermediate value theorem because we're assuming the first derivative is continuous. Now, it's possible that maybe the average speed is happening at the very end. And so I'm not going to get into situations like that. All I really need typically is that there is some point. And so often, to be safe, you will, as was remarked, put in closed brackets here. So you allow the possibility that it happens at an endpoint. But I like the proof by story. So intermediate value theorem, if always below average speed, how could that be the average? And in this way, at least something is written on the board for the people watching. Every now and then, the audio completely fails. And I have, of course, no way of knowing if the audio is failing as I'm lecturing. It happened once or twice this semester. OK, so are we all happy with the intermediate value? The intermediate value theorem and the mean value theorem. So the first thing now is, as a consequence, we have the poor mathematician's Taylor theorem. So Taylor's theorem is that if I give you a nice function can be written as a series expansion. So the theme today is to talk about sequences in series. And the idea is the more terms you take, hopefully the more accurately you should be able to approximate your function.
Sorry, I have a question.
Yep.
Wait, how can it happen at the end? Like if the function levels out or something?
Yeah, I mean, you could probably come up with some strange thing. And so just to protect myself, I'm putting in like that. As a nice exercise, can you come up with a function where the only place it happens is at the very end? One of the proofs I normally like to do for that is I'll just, so let's say you have your function f of x. So this will be a mean value theorem sketch. So I'll see if I can do this live. This illustrates a really good proof technique. Rolle's theorem is the mean value theorem, except in the special condition that f of a equals f of b equals 0. So let's say we know Rolle's theorem, which is f of a equals f of b equals 0. Interestingly, I heard that Rolle was a doubter of calculus, which makes it amusing that the only thing people remember Rolle for is a calculus theorem now. But there were some issues with the foundations of calculus. So imagine we know the theorem is true in the special case when f of a equals f of b equals 0. So now I give you some new function. Let's start off with some function g of x. And let's assume g of a and g of b are not both 0. So I can't use Rolle's theorem. What I want to do is I basically want to subtract something so that I have a new function that is 0 at the endpoints and then apply Rolle's theorem. So if I looked at g of x minus g of a, if I now plug in x equals a, this is going to be 0. But if I now plug in b, I get g of b minus g of a, which is not necessarily 0. So I want to subtract off g of b minus g of a, but I only want to subtract that off when x equals b. When x equals a, I don't want to subtract off anything. So I can multiply this by x minus a over b minus a. And now, if I call this new function f, notice f of a is g of a minus g of a, and then this will be 0. So f of a is just 0. And if I look at f of b, we get g of b minus g of a, and now we'll have b minus a over b minus a, that's 1. We'll get g of b minus g of a. We also get 0. So we've subtracted off basically a straight line. And now we know Rolle's theorem, there is some point where f prime is 0. So Rolle now tells us that there exists a c such that f prime of c equals 0. Well, what's f prime of c? F prime of x is just g prime of x. G of a is a constant. This is a constant. And the derivative of x minus a over b minus a, that's just a very fancy way of just taking x over b minus a, which is b minus a. So I get g prime of x minus g of b minus g of a over b minus a. And now we're told that there's some special point c where the first derivative equals 0. So 0 equals f prime of c is g prime of c minus g of b minus g of a over b minus a. And now we just bring that over to the other side. So this is to really highlight to students, reduce it to a simpler problem. Make some simplifying assumptions for notation. Let's just do the case where f of a equals f of b equals 0. And if we can do that one case, we can do all the other cases. As you go further and further in mathematics, you have a veritable alphabet soup of variables and subscripts and whatnot. And it can be really hard to see what's going on. Try to look at a simple case, really understand what's going on from that simple case, and then build from that. And so here, we now get it. Yes?
So Rolle's theorem, can I just
Yep.
do this?
Yep.
When it's equal to 0?
It's when f of a equals f of b equals 0.
F of a equals f of b. Like if it's
So you could actually do f of a equals f of b.
That's still Rolle's theorem? Because in our textbook that
Right.
we use, it says that the Rolle's theorem is just as long as f of a equals f of b.
So they are essentially the same. If they're the same,
It's the same, but
right,
I don't-
right.
Because then you wouldn't have to do this whole extra piece, I don't think.
Wouldn't
Because if f of a equals f of b equals some constant, some number,
right.
then you wouldn't have to go through this whole thing.
You would still have to go through this part because now I'm assuming I have 2 points that are not the same. If over here for Rolle's theorem, if I allowed that to equal 5 instead of 0, it would be absolutely fine. Because all you're really doing is you're shifting the whole function up. So you're not changing the shape. What this is really doing is we're adding a linear pollution to our function. Or we're subtracting a linear pollution and dragging it down a little bit. And so in terms of a good way to phrase Rolle's theorem, I agree that it would be much better to say, imagine f of a equals f of b. And then if you had that, then you'd be done. And then this would just be the special case when they happen to be 0. So this is proving the mean value theorem if we know Rolle's theorem. So Rolle's theorem is the special case when the average speed is 0. And so if you can then prove Rolle's theorem, then you get the mean value theorem in general. But you still have to do that one special case. So then just very quickly, so let's do Rolle. Let's roll. Okay, so here's A, here's B. Without loss of generality, there's 2 cases. Either my function is identically 0 from A to B, in which case there's nothing to do, or at some point it's positive, or at some point it's negative. Well, if it's Negative at some point, I could just multiply the function by -1, it's positive, or I can just say a similar argument and just move my hands like this. Doesn't really matter that much. Let's assume that at some point the function's positive. So at some point, the function is positive. The first derivative, if the first derivative is positive, you're increasing. If the first derivative is negative, you're decreasing. I start off at 0, and at some later point, I become positive. So there must be some point in between these two where my first derivative is positive. So maybe there's some point here where f prime is greater than 0 right there. I end at 0. I have to go down. So there has to be some point, maybe it's here, where f prime is less than 0. And then the derivative is continuous. So then there must be some intermediate point. So this is a way to prove Rolle's theorem by using the intermediate value theorem. And now once you have that in that case, now you can get it from the following. And I really like this idea of trying to break things into a simple case, understand the simple case, and then go from there. Is there a bell that's ringing at 9:08? Or what was the
9:38.
Oh, 9:38. Okay.
9:33.
9:33. Okay. Okay. So I was trying to time this to end at exactly 9:08. No, that's fine. That's fine.
Perfect. Ring.
Ah, there we go. All right. So that means if you guys can be on, let's do the fundamental theorem of calculus by 9:38. You know, this is one of the major results in all of mathematics. 20 minutes should be more than enough time. So I can't, this is the problem with, such a long wait. If I really cared, I would have watched all the videos again. Only once in my life has someone come up to me and asked me for the area under a curve. Yeah. This is what the fundamental theorem of calculus is. The area under the curve is the antiderivative of b minus the antiderivative of a. One of the reasons we care about this is frequently the area under the curve is the probability of an event. And if we can calculate these areas, we can calculate probabilities of events. So fundamental theorem of calculus. We'll do at least 2 fundamental theorems today.
So is it true to say that most of the applications for this is for statistical reasons?
A huge amount is for statistics, mathematical modeling, a lot of things in physics or chemistry. You need to calculate what's the probability something happens. And areas under curves are probabilities events happen. And so if I have the following situation, where here's my function f of x, then the area under y equals f of x from a to b is f of b minus f of a, where big F is any function whose derivative is little f. And we often denote this by the symbol integrating from a to b of f of x dx. And by definition, this means, well, this is where you have to be very careful. This is denoting the area under the curve. The content of the theorem is that the area under the curve is the same as the antiderivative at b minus the antiderivative at a. All right, clock is running now. All right, so we will prove the fundamental theorem of calculus in 20 minutes.
We'll come back after that break.
No. Whenever I give blood or anything and I'm drugged, I always check, can I prove the fundamental theorem of calculus? And I remember once at Brown, I was having trouble. I said, okay, I'm going to just stay here a little bit longer. It shouldn't be taking me this long to prove it. So I'm going to do the special case a equals 0, b equals 1. Okay? We're going to chop up the interval. So 1 over n, 2 over n, k over n, k plus 1 over n. And I'll call that xk. I'll call that xk plus 1. And so we have our function f. So I'm going to assume f and f prime are continuous. And I'm going to assume f and f prime are bounded. So what it means to be bounded is there is some number b such that no matter what input you give me, the value of my function is at most b. Not every function we integrate is bounded. If I give you the function 1 over the square root of x, and I ask you to integrate this from 0 to 1, this function is not bounded, but it is integrable. I've only got 19 minutes now. I'm going to assume bounded. You can remove this assumption, but let's just leave this for now. So we're going to form 2 sequences. That's the theme for today, sequences and series. We're going to form the lower sum, and we're going to form the upper sum. So on each interval, And I'm going to just really magnify. Here's xk, which is k over n. Here's xk plus 1, which is k plus 1 over n. Here's my function. OK. And then what I want to do is I want to approximate the area. I will look at what point is my function largest. And I will look at what point is my function smallest. So this is a little bit tricky. How do we know such a point exists? And so this is where you can do some real analysis and whatnot. For now, I'm hoping you will not be too upset. I'm just going to assume there is some largest value. Because the function is bounded, I can also just take my bound and just start moving down and say, when do I first hit? And then that will give me my largest value. And so what I can do is I can take the largest value, and that will give me a rectangle. And the area under that rectangle will overestimate, or it will either be exactly right or will overestimate the true area. I can take the place where the function is smallest, and I can form. So I'm going to use L sub k for the lower point, and U sub k for the upper point. And we know the following. So I will not say this out loud. Times f at this point times 1 over n is going to be a overestimate for the area. F at lk, that one I can say, times 1 over n will be an underestimate for the area. And so the true area of the kth piece will be sandwiched between the two. So I'm going to define the upper sum with n partitions to just be the sum k goes from 0 to n minus 1 of these upper partitions, and the lower sum to be the sum k goes from 0 to n minus 1 of flk times 1 over n. And we know the true area sits between these. So the question is, how close is the upper sum and the lower sum? Well, let's look at their difference. So if I look at un minus ln, I'll put the absolute value, but I don't really need the absolute value because un is larger than the lower sum. This is going to just be less than or equal to 1 over n, the sum k goes from 0 to n minus 1 of f of uk minus f of lk. Actually, it's going to be exactly equal. Now, if you look at this, I have a 1 over n here. As n gets very, very large, this is great. This is going to 0. And because I've chopped things up into a small interval, these should be very close to each other, so this should be small as well. So I have two things that are small. Unfortunately, I have a sum with n terms. And it's possible that that sum with n terms could be so much that it counteracts that 1 over n here. So what theorem should I use here to understand this difference? So what's the title of this lecture? No. This is the Friends lecture. The one with the mean value theorem. When in doubt, always go to the mean value theorem for this part of today's festivities. Okay? Use the mean value theorem to estimate this. By the mean value theorem, this is 1 over n, the sum, k goes from 0 to n minus 1. And then over here, I'll just get f at some intermediate point ck times the difference. Now I've got to be a little bit careful because I don't know which point comes first or second. So I'll have to just write, I'll write it like this, uk minus lk. And that's the first derivative at some point like this. And now if we assume that our first derivative is bounded, how far apart can uk and lk be? What's their maximum separation? 1 over n. So this would be less than or equal to 1 over n from this times our bound for the function times a sum k goes from 0 to n minus 1 of 1 over n. And this is where the mean value theorem saves the day. This has to be small, so small that even when I sum it n times, it's still small. So the n here cancels the n over here, and this is going to be b over n. And that goes to 0. So this proves that the upper and the lower sums converge. The difference between them is getting smaller and smaller and smaller. What's interesting is the upper sums don't have to be strictly going down. They'll only go down, and this is an annoying point in calculus, if you do a refinement of the partition, where you put your next point as a point between two partition points. Once a partition point, always a partition point. What people will frequently do is n will be a power of 2. You'll first do split it in half, then fourths, then eighths, then sixteenths, so you have a refinement. If you have a refinement, it's a lot easier. Otherwise, things could actually change, and the upper sums may not go strictly down. So is everybody comfortable that the upper and the lower sums are converging to a common value?
Can you just do that last one?
Sure. So by the mean value theorem, we often write it as f of uk minus f of lk divided by uk minus lk is f prime at some intermediate point. So I've just multiplied the denominator here. So it's f prime of ck times this. So it's basically saying there's some point here, I don't know where it is, where the value of the derivative at that is the average slope. And that allows us to just show that this difference is small. So we now know that un and ln converge to common value. What is the only value they could converge to? So un and ln converge to a common value. What must that common value be? I'm sorry? Not the average height, because remember, un is now the sum of all the upper sums for each subinterval, and ln is the sum of all the lower sums for each subinterval. It has to converge to the area, because we know the lower sum is always less than equal to the area, is always less than equal to the upper sum. So if ln and un converge to a common value, the only thing it can converge to is the area. So one way for you to calculate areas is to subdivide, find where the function is largest. Okay, this is a real pain. So now we're going to calculate the area another way. Plenty of time, won't even be close. Okay, so now here's something that's fascinating. Ln is less than equal to the sum, k goes from 0 to n minus 1 of f of wk times 1 over n is less than equal to un. If wk is in the interval xk plus 1. What I'm basically saying is just choose any point you want. Any point you want. It's got to be the value of the function can't be smaller than where it's the lowest. It can't be larger than where it's the greatest. It's got to be somewhere in between. So if I just sum the area of all those approximations, it's going to lie somewhere between the upper sum and the lower sum. And I now have the freedom to choose these points wherever I want. Okay? So now, what theorem should we use? Okay, let's use mean value theorem. So by the mean value theorem, but now we apply the mean value theorem not to little f, but to big F. Big F at xk plus 1 minus big F at xk is equal to the derivative of big F at some special point. Let's call it vk, times xk plus 1 minus xk. What's xk plus 1 minus xk? It's 1 over n. It's the length of the interval. And so we get f of xk plus 1 minus f of xk is, and the derivative of big F is just little f of vk times 1 over n. All right, I think I know what I want to choose for my wk's. Let's choose them to be these magic points vk. Okay? Now this is where things get fun, or more fun. So f of 1 over n minus f of 0 is f of v0 times 1 over n. F of 2 over n minus f of 1 over n is f of v1 1 over n. F of 3 over n minus f of 2 over n is f of v2, 1 over n, dot, 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 and then f of n over n minus f of n minus 1 over n is just little f of vn minus 1 times 1 over n. And what's nice is if we add these, the 1 over n cancels. The 2 over n cancels. Everything cancels. So this is a telescoping sum. And so telescoping sums are really nice. All that is left is the first and the last. So we get, on this side, this is just f of 1 minus f of 0. Oh, that's the quantity we wanted. And on this side, we have a bunch of areas. So we have the sum of f of vk 1 over n. K goes from 0 to n minus 1. So what we could do is we now get that ln is less than or equal to f of 1 minus f of 0 is less than or equal to un. And what's great now is this part here doesn't change as I change the partition. It's a fixed quantity. It's f of 1 minus f of 0. So as n gets very, very large, ln and un converge to the area. Well, given that this is always sandwiched in between the two of them, this must actually equal the area. And so this is the proof of the fundamental theorem of calculus. So we can check. I think this was not even 20 minutes. So the question is, where are we really hiding things? So the real trick was over here. And it's, which statements seem reasonable but are not. I'm saying that there is some point where the function is largest. And there is some point where the function is smallest. If I give you the function, 1 over square root of x, well, it's blowing up. Well, the function's not continuous. And so I always like to point out to my students where I'm lying to them or hiding things from them or trying to sweep things under the rug. This is the difficult part here. And there's a beautiful theorem in analysis that says if you have a continuous function on a closed interval, it attains its maximum at some point, and it attains its minimum at some point. We can try to do the arguments we did with the divide and conquer before. We're assuming the function is bounded and the function is continuous. So take the bound and start moving the bound down as far as you can until finally it hits. There should be some point where it's largest. What if it wasn't largest? Well, then the function would have to somehow be increasing more and more and more. There would have to be a hole or something. So this is the part that really needs to be justified. The rest is just nice applications of the mean value theorem. And it illustrates one of the strangest concepts of pure mathematics. We can prove something exists, but not know where it is, but that's often enough. And so here, there is some point ck. There is some point vk. Where is the point? I don't know. It's somewhere in the interval. And we don't really need to know where it is, other than it exists. And from its existence, we can deduce certain things. There is a choice we can make. And if we make the right choice, then this sum is exactly equal to the area. It becomes a really interesting question. How would you actually find these points vk? No idea. There are things you could try to do. We have ways of trying to solve equations like this. But fortunately, we don't need to know where it is. At the end of the day, this is just auxiliary helpful points. Probably the best thing to compare this to is geometry when you draw the auxiliary lines. At the end of the day, the auxiliary lines don't really matter. But by putting them in, it helps you put things in context. So I would say that this is very similar to the auxiliary lines. Okay. Any questions on the fundamental theorem of calculus?
Yeah. Tons.
So the next time you have massive amounts of drugs pumped into your system, this is a way you can check to see when they're out.
So saying that the function is bounded is the same as saying that the extreme value theorem applies? Is that true?
Well, if the function is continuous on a closed interval, it's automatically bounded.
Okay. So
there's a whole chain of results where you have these sharpened concepts called uniform continuity, where in compact sets, that in situations like this, you will know that these points exist. And there are a lot of things where, sadly, we don't necessarily know that there is a optimal choice. I'll end with a game. There's a lot of different games. Have we done any dot games yet? Okay, so I've done some of these games with my kids' classes and some of them with my college students. I actually do the same games in both situations. I don't believe in age-appropriate mathematics. Unfortunately, I've been visiting my kids' classes for too many years. My son is in 5th grade, and his friends now know that when I'm making certain, oh no, you moved there, that I'm probably just pretending. So here is one version of a dot game. You have a bunch of dots, and they're in a nice rectangular grid. And then on your turn, you choose a dot, and you eat all the dots from there up and all the dots from there to the right. So for instance, if I choose this dot, I would eat all of these 6 if I chose that dot. If I chose this dot, I would just eat the highest row. And 2 people alternate. Whoever eats the last dot wins. Is the game interesting? No, what would you do? Yeah, go down to the bottom. Okay, so if the winner is whoever eats the last dot, the game is pretty boring. All right, so how should you determine who wins? Okay, is it whomever? Whomever eats last loses. Okay. Now the game has at least the potential of being interesting. So do you want to go first or second? So the first question is, do you think there's a winning strategy? Yes. Why is there a winning strategy? So that's not bad. This is sadly how my son's friends reason. But why must there be a winning strategy?
Only from my experience with that game with NIM.
Right.
Thinking some way, and at the end, that choice where you have this or this plus this, and so
So we've seen games before that have winning strategies. Does chess have a winning strategy? Supposedly. But is it possible that chess might not have a winning strategy? Chess can end in a draw. What's the classic game that should end in a draw if people play it well? Tic-tac-toe. Right? There is no winning strategy in tic-tac-toe. But here, somebody's got to win. So there should be a winning strategy. I will prove to you that player 1 has a winning strategy. I don't know what the winning strategy is. I will just prove that a winning strategy exists. Okay? Imagine player 1 has a winning strategy. Then player 1 has a winning strategy, and we're done. Okay? So case 1, player 1 has winning strategy. Done. All right. What's case 2? Player 1 doesn't. So player 1 goes here. It's now player 2's turn. Player 2 has a winning strategy. Okay? Player 1 could have played that. So imagine player 2's winning strategy in this situation is to go here. Then all player 1 has to do is, oh, well, if that's player 2's winning strategy once I go here, I've changed my mind. Do over. Or whatever the kids will scream. I choose to go here now. Change move. So I have now proven to you that player 1 has a winning strategy. How useful is this? So you know you want to go first, probably. So this is very different than the mean value theorem. In the mean value theorem, I proved the existence of the point, and we were able to do stuff with that. Okay.